Welcome to our 6th training session, where we will demonstrate how to configure general purpose I/O pin as an interrupt input. We will then write an ISR handler for this interrupt, implement software debouncing, and increment a software counter, and display the count value on LCD. Any embedded system project involves 3 important steps. The first step, we select embedded C as our programming language. The second step, LPC 2148 based evaluation board, and the LC module. Programs written in C are readable and easy to debug. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. Let us now start building our software components for each on-chip peripherals we require for this project. Crossware Wizard will help us too, configures the device components present in the ARM microcontrollers. All the device peripherals are nothing but memory mapped registers. The Wizard peripheral dialog boxes are exact replica of the data in ARM reference manuals. The Wizard configuration ranges from high-level function selection of a peripheral, all the way down to the definition and purpose of an individual bit field in a memory-mapped register. The VPB divider determines the relationship between the processor clock CCLK and the clock used by peripheral devices, the PCLK. The default condition at reset is for the VPB bus to run at 1/4 speed. The VPB divider register is configured using first 2 bits, allowing 3 divider values. LPC 2148 has 2 32-bit general purpose I/O ports. Port 0 has 30 I/O pins and 1 output-only pin. Port 1 has 16 pins, which can be used as I/O pins. The I/O direction register individually controls the direction of each port pin. A 0-bit indicates input, while a bit set to 1 implies the port pin as output. When a bit is set to 1 in the I/O set register, the corresponding pin is set to high. When a bit is set to 1 in the I/O clear register, the corresponding pin is driven low. The current state of the any pin configured as general purpose I/O can be read from I/O pin register, regardless of pin direction. Binary data written to I/O pin registers are shown immediately on the output pins. Each pin in LPC 2148 is multifunctional. On reset, all the pins are configured as general purpose input pins. Our demo board has a switch wired to P0.20. Any pin can have a maximum of 4 functions. Hence, in order to select one of the 4 functions, 2 corresponding bits of the pin select register needs to be configured. Hence the first step is to configure P0.20 as a dedicated external interrupt pin. Pin select 0 register is used to configure first 16 I/O pins of port 0, while pin select 1 register is used to configure bit 16 to 31 of port 0. The external interrupt function has 4 registers associated with it. The external interrupt register has 1 bit specified to each interrupt input. These bits contains the interrupt flags and are set when an interrupt occurs. When an interrupt occurs on port pin P0.20, the bit in location 3 is set. Writing 1s to bits 3 in external interrupt register clears the P0.20 interrupt. The external interrupt pin is edge sensitive if the mode register bit is set to 1, and is level sensitive if the mode register bit is set to 0. If the mode bit is set to be level sensitive, then the polarity register determines if an low level or high level signal generates an interrupt. If the mode bit is edge sensitive, then the polarity register determines if an rising edge or a falling edge can trigger an interrupt. The Crossware Wizard generates the required configuration code. When we select, pin ports are 0.20, for external interrupt function, then, a logic level low or logic level high, can generate an interrupt. This mode is called level triggering. While an interrupt so generated, because of a rising edge of the signal, or falling edge of the input signal, is called edge triggering. So when an interrupt occurs, it asserts a corresponding bit, in the vector interrupt controller. This interrupt is propagated, only if the corresponding bit, is set in VIC interrupt enable register. If the VIC interrupt select register bit, is set, then this signal can be, classified as FIC or IRQ. If the interrupting signal is IRQ, then it can be assigned, to one of the 16 slots, with slot 0, having the highest priority. We can assign timer, to slot 0, and external interrupt, to slot 1. The vector address register, slot 1, stores the address, of external interrupt subroutine. This completes, all the requirements, of setting interrupt, for port 0.20. The next important hardware block, will be the timer and counter module. If this hardware block, is configured, to counts peripheral clock pulses, it is called timer. When this block, counts pulses, on external input pin, it's called a counter. The first step, is to configure the block, as a timer or a counter. The count control register, is used to select between, timer and counter. If the first 2 bits, of the count control register, is 0, then it configures, the hardware as a timer block, else it operates as a counter. If the counter mode is selected, these 2 bits selects, the external signals, pulse edge used, for counting operation. The pulse edge can be a rising edge, or a falling edge, or both the edges, can be used to increment the counter. The next 2 bits, selects one of the 4, external counting pulse, for incrementing the counter. We will be configuring, the timer counter block, as a timer. 2 bits of the timer control register, controls the 32-bit counting operation. If the bit 0 of TCR is set, the counting operation is enabled. If the bit 1 of TCR is set, the counters are reset to 0, until the bit is cleared. To generate a precise time delay, we use match registers. There are 4 match registers, named MR0, MR1, MR2 and MR3. The match register values are compared with the 32-bit timer counter TC, and if a match occurs, the match control register, MCR, can be programmed, to generate an interrupt, or reset the 32-bit timer counter or stop the counting operation. We will use the Crossware wizard, for generating code, to load the match register MR0, for a 1 microsecond interrupt, and reset the timer counter TC. The timer interrupt, is routed to, vector interrupt controller. The first step, is to enable timer interrupt, in VIC interrupt enable register. The second step, is to select timer interrupt, as IRQ. The third step, is to use slot 0, for timer interrupt. This sets the VIC control address 0 for timer, and VIC address 0, for timer ISR. The Crossware wizard, generates VIC programming code. The aim of this lab, is to demonstrate the working, of external interrupt. We will be incrementing, a key press counter, to bounce the key press and display the count, on the LCD module. The LCD module interfaces, with the processor, using 8-bit data bus, D0 through D7, and 3 control lines. The 3 control lines are, register select, register read write, and an enable pin. The LCD module has 2, 8-bit registers, which can be controlled, by the processor. The register select pin, when low selects, the command register. The processor can then issue, various commands like, LCD configuration, clear display, home cursor etc. When the register select pin is high, the data register is selected. The processor can send, ASCII data which are displayed in the LCD module. Using all these, software components, and hardware driver, we will demonstrate, the working of external interrupt. All C programs starts from main. Embedded systems interact with the external world using input-output devices. Hence, in our first function call, we initialize general purpose port pins. We configure first 16 pins of port 0 as output. In this lab, we have connected and switched to P0.20 pin. Hence, the second function call, we set up the external interrupt input and the associated interrupt subroutine. The third function call, we initialize timer 0 and generate timer interrupt every 1 millisecond. The timer will be used for generating time delays, for LCD module interfacing, and switch debouncing. The fourth function call initializes the LCD module for displaying 2 lines of data. After this, we enter an unending loop where we increment and loop counter each time external interrupt key switch is pressed. In our first function call, we initialize first 16 I/O pin direction to be output. The first 8 I/O pins drives the LCD data bus, while next 3 pins will select LCD registers using register select bit RS, write and read LCD registers using read-write bit RW and the enable bit E. In our second function call, we configure general purpose I/O pin 0.20 as an external interrupt input. This requires us to select alternate function for port pin 0.20. The first 16 pin of I/O uses pin select 0 register, while pin select 1 register needs to be set up for pin 20 alternate function. The external interrupt mode register is set up for edge triggering. The polarity register is configured for falling edge trigger. This external interrupt, when triggered, gets propagated to vector interrupt controller module. We need VIC interrupt enable register, bit number 17 to be enabled for external interrupt. The VIC interrupt select register is configured for IRQ. We assign slot 1 for external interrupt and set up the VIC vector control 1 register to enable interrupt and route external interrupt to slot 1. The vector address 1 register has the ISR address for external interrupt. Crossware wizard using point and click menu will generate relevant codes. In the next function call, we initialize the timer block. The first step is to configure the block as a timer. This would mean the clock source will be the on-chip peripheral clock. The next step is to enable the timer to count by setting the timer control register TCR bit 0 to 1. We then go ahead to load the match register 0 so that it can generate a 1 microsecond interrupt and reset the timer counter register. The Crossware wizard works out the value for us. We then configure the vector interrupt controller to enable timer 0 interrupt and interrupt to be of IRQ type. We define slot 0 for timer interrupt by setting vector control 0 for timer 0 and vector address 0 pointing to the ISR routine. This completes the timer initialization routine. We will be using LCD to display our lab results. LCD has 2 registers, one to accept commands, and the second one to display message. The set of commands required to configure the LCD are stored in the command 8 array. The message pointer is loaded with the address of the first instruction in the command 8 array. The data in the command 8 array is loaded and transferred to the LCD module by setting RS bit low and toggling enable E bit. The interrupt subroutine for external interrupt input is quite simple. An interrupt indicates that the switch is pressed, hence the key hit flag is set to 1. We are yet to debounce this key press, hence the debounce flag is set to 0. We acknowledge the external interrupt by clearing the interrupt flag set in the IR register by writing a 1 to it. We also clear the VIC system by writing a 0 in the vector address register. This completes the ISR for external interrupt. In the timer interrupt subroutine, we very well know the time interval is 1 millisecond. Hence we decrement all time-dependent variables. We enable timer for the next 1 microsecond interrupt by clearing the match 0 bit set in the IR register. Similarly, we signal the VIC end of timer routine by a dummy write to the vector address register. We normally take for granted that a mechanical switch is an ideal on and off device. But in reality, the switch behavior is like dropping of a ping pong ball. The switch state oscillate between on and off multiple times before settling in its new state. Normally a switch ceases bouncing in less than 5 millisecond, but a switch state counter will increment multiple times. Hence, debouncing switches using software is the only way to go. We use a timer, wait for a delay time, a constant for external interrupt, and then go ahead to increment the external switch count. The last function call, show message, displays the switch press count on the LCD module. On each key hit, we check if the key press is debounced or not. If the debounce flag is not set, we implement software debouncing and then increment key count variable. The key count variable is first converted to decimal value before displaying count message as ASCII values on the LCD module. The last function call, write LCD, uses the message pointer to display key press count by setting register select bit high, and then go ahead to toggle the enable bit to strobe the ASCII message. The write LCD loops until the last ASCII byte.